Have you ever just sat perfectly still, like totally motionless? Well, welcome students. Today, in this explainer, we're going to completely dismantle everything your everyday intuition tells you about what it actually means to be still. We're diving deep into the foundational science of kinematics, specifically section 3.1, focusing on rest and motion. And honestly, by the time we wrap this up, you're going to realize that stillness is basically a brilliant illusion.
Let's kick things off with a deceptively simple question. When do we genuinely say a physical body is at rest? Just picture a textbook sitting quietly on the table right in front of you. Your brain automatically registers it as stationary, right? You'd probably say, well, if it doesn't change its physical position as time passes, it's at rest. But since we're getting into the rigorous scientific details of kinematics here, we have to meticulously test that assumption. Is that specific book actually unchanging in its position?
To figure that out, let's completely change our vantage point. Imagine we transport ourselves all the way to the moon. A pretty breathtaking view that the Apollo missions made a reality for us. Suddenly, our kinematic reality flips upside down. From up there, we can clearly see the Earth spinning on its axis and rocketing through space. And because the Earth is moving, while the room, your table, and that supposedly stationary book, they are all continuously changing their spatial coordinates too. So the book is at rest when you're looking at it from the room, but it's unequivocally in motion when observed from the moon.
Which brings us to a really crucial, kind of mind-bending point. Your text lays it out perfectly. Motion is a combined property of the object under study and the observer. I mean, really think about that for a second. There is absolutely no objective meaning to the words rest or motion without a viewer. The book moves relative to the moon, but it's at rest relative to the table. This thought experiment reveals a massive foundational law of physics. Motion cannot exist in a vacuum. It is entirely relative to who or what is actually doing the observing.
Let's look at a super vivid example straight out of figure 3.1 to really hammer this home. Imagine a robber suddenly bursts into a train compartment that's barreling down the tracks at high speed. He whips out a pistol and yells at the terrified passengers, "Don't move, stand still."
Now, what's really fascinating here is the dual reality this creates. So the robber, standing right there in the aisle, those passengers who froze with their hands up, they're perfectly at rest. Their relative velocity to his pistol is strictly zero. But to a bystander watching from the side of the rail track outside, those exact same passengers are rocketing forward at high speed along with the train. It's the exact same moment in time, but we have two completely different states of motion, and it depends entirely on the observer.
Okay, so how do we translate these philosophical thought experiments into rigorous, hard science? Well, to mathematically locate a particle and analyze its kinematics, physicists need a highly specific mathematical system. We call this a frame of reference. It's essentially the foundational coordinate system you absolutely have to establish to anchor your perspective before you can even begin calculating things like velocity, displacement, or acceleration. It's the bridge between a subjective observation and hard objective data.
So how do we actually build one? A really convenient way to construct this frame of reference is by using a Cartesian coordinate system. We basically just choose three mutually perpendicular axes, the x, y, and z axis. This lets us pinpoint the precise three-dimensional spatial coordinates of any given particle. But space alone isn't enough, right? Because kinematics is fundamentally the study of motion over time. So we absolutely must lock a clock into our frame to meticulously measure the passage of time alongside those spatial coordinates.
Armed with this specific coordinate frame in our clock, we can now scientifically define motion in three definitive steps. First, we continuously check the x, y, and z coordinates of our target particle as the clock ticks forward. Second, if all three of those coordinates remain completely unchanged as time goes by, boom, we can officially declare the particle is at rest with respect to this specific frame. But third, if even one of those coordinates changes with time, the body is officially in motion relative to our chosen frame. See? It removes all the guesswork and replaces it with pure mathematics.
Now, here is one of the most fascinating and honestly liberating quirks in all of kinematics. There is absolutely no universal rule restricting your choice of a frame. None. We have complete scientific freedom to pick whichever frame of reference is most convenient for the specific problem we're trying to solve. The math? It's always going to work out perfectly, provided you remain strictly consistent within whichever frame you originally picked.
Let's apply this idea of convenience to another train example. Say we're sitting inside a moving train.
It is super convenient to choose a frame attached directly to our compartment. Let's call it the train frame. In this frame, the coordinates of a suitcase sitting up on the upper berth do not change with time, assuming the train is keeping a steady speed. So the suitcase is at rest in the train frame, but look out the window. The stations, the trees, the electric poles, their coordinates are changing rapidly relative to your compartment. So scientifically speaking, they are physically moving through your train frame.
This scientific reality actually perfectly explains why we use certain phrases in everyday life without even realizing the physics behind them. Like when passengers on a moving train say things like, "Oh, Bombay is coming," or "Pune has already passed," they're actually making perfect kinematic sense. In their highly convenient train frame, those massive cities are genuinely translating toward or away from them. It's so cool how our everyday language naturally adopts these convenient frames of reference.
Now, as you work through physics problems, you're frequently going to encounter something called an implicit frame. Sometimes the choice of the frame of reference is just so incredibly obvious from the context that the textbook doesn't even bother mentioning it. For instance, when we say a car is traveling at highway speeds or a parked rickshaw is stationary, we are implicitly assuming a frame firmly attached to the road. It's essentially the default setting for our brains. But as physicists, we always need to be aware of what implicit frame is being used to anchor our coordinates. So pulling all these mathematical and observational threads together, this whole explainer really boils down to one monumental truth. And honestly, it's a concept that should fundamentally reshape how you understand the universe. Nothing is in absolute rest or in absolute motion. Every single calculation of displacement, velocity, or acceleration depends entirely on the reference frame you select. In the grand scope of our cosmos, absolute stillness, it simply does not exist.
Which brings us to our final thought. Since there is literally no absolute stillness anywhere in the universe, it all comes down to perspective. So, the next time you sit down to solve a physics problem, or even just observe an object in motion in everyday life, take a moment to look at the system and ask yourself, whose perspective am I viewing this from? Where are my axes drawn? Because if motion is truly just a matter of perspective, how much of what we see every day is just an illusion of our chosen frame?